From the beautiful southern studios of Way Happy, this is Mr. Meyer in section 3.2, exponential and logistic modeling. Now, we've seen exponential graphs, and we've noticed that they are either growth or decay. And so we can model a lot of real life situations after that. And so here is a beautiful equation that if you know that there's a constant rate of change for anything really, if you can model it, if you know it's increasing, let's say 10% every minute, I can make an equation for it. If it's a constant 10%, if it's decreasing at 5% every year, I can make an equation for it, or every 10 years, I can make an equation for it. So the cool thing is, or maybe it's doubling every 5 years. I mean, any equation that is constant, I can do it, or at least I can make a model for it. So what are the parts of this equation? Well, P sub 0 is your initial value. So at some point you had to know how much you had, whether it's money or population of jellyfish in the ocean. You had to know that on this day we measured it and this is how many we had. And then in years after that, we started to concentrate how many there were. And now I can tell you what the rate of change is. So this is the rate that is increasing or decreasing. You always want to make sure you write that as a decimal. Time, that is the time for the rate. Like it is 5% every year. So T would be in years, or 5% every minute, then T is in minutes, or 12% every second, then T is in seconds. And then this right here will tell us our population at that given time. So if you want to wait 5 years down the road and your equation's in years, then T is a 5 and I can tell you the population. All right. So remember all the good stuff. Anything that has an exponent, that is your base. If that's bigger than 1, it's growth. If it's less than 1, it's decay. All right, let's look at this first one. First thing I'm going to look at is, oh my gosh, there's the exponent. This is a very important value right there. If it is bigger than 1, it is growth. If it's less than 1, it is decay. So I'm looking at that and I'm like, oh, this is bigger than 1. This is a growth graph. Something is growing. And I can tell you that this was the initial value. So whatever they counted 1 year, that's how many they had of whatever's, right? Let's say it's money. You had $786,000, $543 in your account, and it's growing at a certain rate. And I can't wait to see how much I have in 5 years or something like that. But that would assume that this growth rate is constant. And what is that constant growth rate? Well, let's see. They want it as a percentage, so we'll find it. But we do know the blue bubble that I have there is 1 plus the rate, right? That's how much it's growing by. I'm trying to figure out that rate. And then I'm going to set that equal to 1.021, and I'm going to solve it. So subtract 1 over, and I get R equals 0.021. Now that's the decimal, so the percentage would be 2.1% increase or growth, or let me know that it's going up 2.1%, meaning the base is going to be bigger than 1, not smaller than 1, because that would be decay. Let's see if we can write an equation in example 2. Example 2 says you have an initial value of 10. These are eagles in Livermore, and they are increasing 5% a year, the number of eagles. So this has been really good news. So could you make an equation? Well, of course, right? Here's my equation. P at a given time is the initial value times 1 plus the rate to the T power. Now I know this is in years, and I know it's 5%. So I know that my rate is 1 plus 0.05. That's the decimal, and that's T in years. And the initial value is 10. And so here's my equation that will tell you the population of eagles in Livermore, T years from whenever we measured it. So say we measured it in the year 2000, then now this is 2015. We would have to do T as 15 to see how many eagles there are here in Livermore now, if they were growing at that constant 5% rate every year, right? So we're assuming that stays constant. And that can be measured. That can be totally measured. You can solve this stuff too. You got to say you got 200 bacteria in a petri dish and it doubles every hour. Could you make an equation for that? Well, of course. I'm going to take my general equation. P sub T equals P0, 1 plus the rate to the T. Now notice every hour, so time is now going to be in hours. So we just got to make sure we know that. Doubling, that's, you take 1 plus the rate. Well, the rate is 100%, right? So what most people would call 1 plus 1 or 2. Hey, wait, that makes sense because doubling is when you multiply by 2. And look what you would do. You would take this original bacteria and you would multiply it by 2, right? That would make it double. Now it's 400. And you would have to do that every hour. So you could put T here, but just realize T is now in hours. So I would want to make sure people know that. So I would tell them it is in hours. So there's my equation, right? That's my equation for this bacteria and what's going on with it. Now I asked a second question. Not only did I ask you to make an equation, but I really asked you to predict when the bacteria will be at 350,000. So I'm just going to set this equal to 350,000. And then I'm going to say, all right, that's not such a bad deal. I will grab my calculator and I reset it. And in Y1, I will put in 350,000, 0, 1, 2, 3. And in Y2, I will put 200 and then times 2 because it was doubling to the x power. Now my window is going to be really gross, right? I mean, look at that Y1. It's got to go up all the way to 350. So I'm already going to hit my window button. I don't know where my X's are going. It's how long is it going to take to hit 350,000? Let's say it's going to take all the way up to 25 hours. I'm not sure. I might have to change my window later. We make it tick marks go by 5. Here's the one I do know though. I got to get up to 350,000. So we'll go from 0 to 360,000. And I will make my tick marks go by, what do you want to do? 20, 200,000s, I guess. I don't know. That's just how often you want it to put a tick mark. Do you want a bunch of crazy tick marks or not? And now I hit graph and there's the 350,000. And then here's the other one. Boom. I can see it right there, right? It's a little past 10. So it's between 10 and 15. It's really close to the 10. So I'm going to call it, even probably less than 11. Well, how do I know for sure? We're going to hit the calc feature. So second calc, and we're going to find the intersection. Now it asks you, what are the two equations that we're asking you intersect? Now I like to use the straight line one as my second one. So it says, is the first curve this one? And I'm going to say, no, up arrow. It's that one. See how I used the up arrow and it changed the equation? Is the first equation this one? I'm going to say, yeah, that's it. Hit enter. Is the second equation that the 350,000 one? I'm going to say, yeah, that's it. And then I'm going to move because when you move on this straight line one, it's a lot easier to find the intersection. And then I'm going to hit enter. And then it's going to say, boom, there it is. It intersects at 10.773139. So beautiful. T is equal to 10.773139. Now that's approximation because obviously that decimal probably went on a lot longer, but that's really good approximation. And I'm feeling pretty good. So in about 10.7 hours. So maybe there was something like, oh, we hit a critical mass at 350,000. Like how much time do we have before this bacteria has covered the entire thing, and so we know we have 10.7 hours to fix this problem, right? Now that is beautiful. Let me ask you one or two questions and then I will come back and see you in a minute. Nice effort on those ones. Now let's talk about, of course, a little calculator, a little regression for you. So if I'm going to go ahead and let me see, find my calculator here. You see this list, this is data, this is population. And so we got our data, we're ready to type it in. So remember what you do is you hit stat and you go to edit. And in list one, you put the years. Now notice what I did, 0, 10, 20. That means that I'm going to use the initial data of 1900 as our initial value. So my time is 0 years since 1900 is 76.2. And I didn't pay attention to what that was. It never says. So we're probably going to say million people. And so now I can go ahead and fill in all that data. So go ahead and pause the video if you want to, because I already typed it in. And now I get them all in. Hopefully I didn't make any mistakes. And then I hit stat, go over to calc, and then I'm going to look for exponential regression. There it is, number 0. Hey, look, our good friend power regression is there too. Power from last chapter. Now I have exponential regression. I'm going to go ahead and hit enter. The X's are in list 1, the Y's are in list 2. If you want your calculator to store the equation in your Y equals, that's what this store regression equation is. It's in the F4 menu. So if I go alpha F4 and I just pick Y1, it'll now put it in Y1 for you if you so care. And then I hit enter and boom, there it is. Look at that. A beautiful equation, 80.867. All right. Y equals 80.867. And then what is it? 101,276. 101,276 to the x power. That's the equation the calculator gave me. Now notice something that freaks a lot of kids out. First off, we notice this is growth, which that makes sense because it's been going up. So that makes a lot of sense. But look at this initial value. The initial value is not the same. That's because it's a model, right? This is not exact, but this models the data very well. In fact, look at our R squared is 99.5. It's a really good model. In fact, I'll even show you, I'll turn on my stat plot and let's see how good that line was. I'm going to do a zoom stat, which is zoom 9. There's all the data. And look at our line just nailing most of those points. So although it's not exactly the same, it models it really, really well. And so if you were to take my equation and put a 0 in it, you would get 80.867, which is not 76, which is not perfect, but it's going to be really close for all those data points. And that's why this is a good model. All right, so we got our model. You could do stuff now, like now that I had it, the calculator type it in for me. Notice I didn't have to put it in there. It's now in Y1 typed in. Great. I'm going to turn off my stat plot real quick in case I need it later. I can go to the table because a lot of kids will wonder, like, why isn't it in the table? Well, it is right now because of the fact that I had the calculator put it in Y1. So you always have to put something in Y1 if you want a table to show up. And now I can go see, like, what would our year be? This is 2016, right? So I could go down to 126. That would take too long. So second table set, I want to start at 126. And if I now go to second table, there it is, 399.57. And we said I was guessing billions because I didn't write it down. So we're going to assume, or millions. I mean, I don't know which one it is. And so what I wish they would have told me, I wish I would have written it down. All right. Oh, and it said due the population 2009. So I guess I should have only gone to, why the heck did I go to 120? What did I pick? 2009 would be 109. Why was I in the 20s? Yeah, good morning. Hope you guys are okay. There's 2009, 322 million, or maybe it's just 322 people in the US. Who knows? All right, nice work. Now let's see if we move on here a little bit. What is going on right here that I can't see this? So quick, shrink the screen. There. How about half-life formula? Half-life formula scares a lot of people. That's the same exact formula, right? You have your initial value there, your P0. The population gets cut in half or whatever it is, gets cut in half. So you're going to multiply by half. Maybe the tricky part is the exponent, but don't let the exponent be tricky. It's just telling you how often to cut it in half. If it was every hour, then you just write T, right? And then make T in hours, and every hour you cut it in half. But what if it's like every 13 hours? That would be weird to tell people, like, you put it in T and you're like, well, just so you know, T is only 1 every 13. It would be too confusing. So the way you actually do it is T is how many hours have passed, but this K value is really what's called the half-life, or how long it takes until you cut it in half. Maybe let me do this example for you. You got some certain substance and there's 10 grams originally, and it gets cut in half every 14 days. So again, here's that formula, right? PT equals P initial and then 1/2 to the T power, but your T power is a little special this time. Here's the population at a given time. The initial was 10 and it gets cut in half. Now look, if I just put T, then it would cut it in half. When T is 1, it would cut it in half. When T is 2, it would cut it in half twice. That's not what I want. I don't want you to cut it in half until T reaches 14. So I divide by 14. So now when T is 1, it's not going to completely cut it in half. It won't, in fact, cut it in half until T gets to 14, because when it does, then your exponent will be 1 and it will finally cut it in half. When T gets to 28, it'll be 2 and it'll cut it in half twice. And that's all half formula is. It's the same exact formula we just used, but we have this little divider saying, hey, just so you know, it takes 14 days before you can actually do whatever's in the parentheses. Got it right? All right, there's your equation. Now I can go ahead and say, when is there less than 1 gram remaining? Well, guess what? I'm going to set this equal to 1, and I am going to grab Sheila and have her graph this for me. So I will get my calculator, and in y1, I'm going to clear this out, and I will put 10 times 0.5 to the, and then I better, oh, I don't need parentheses, yay, x over 14 power. And then down here, I'm going to put 1. And then I'll, for you guys who love your Zoom Fit, I will try Zoom Fit and then probably get angry and say I'm never going to use it again. Zoom 0. And here's our Zoom 0. There it is. That bad boy. And there's the one. Oh, that worked out really nicely. I can see the intersection is right about here somewhere. So second, calculate. I would like you to find the intersection. Do the gross one for the first curve. Yes. Do the pretty one for the second curve. Yes. I can kind of cursor over to where I think the intersection is, right about there at 44. And it's actually at 46.51. So at 46.51. 0.51 is when it'll hit, it'll hit that beautiful 1 gram. And so therefore I can tell people that it's going to take 46.5 days in order to reach 1 gram. So let's say 47 days, you'll be less than 1 gram. All right, what about this last bad boy? This is a logistic. Now we've done all this about logarithms or exponential. I'm sorry, all this, don't say logarithms, that was bad. All of this about exponential graphs. And you can see this looks like an exponential graph, but then again, it flattens out because it hits its limit to growth. C is that numerator right there is the limit to growth. That's how much it can handle, right? That's how much the school can handle. That's how much a city can handle. That's how much room a classroom can handle, right? So look at this exponential growth. Notice it's stopping right here. 1, 2, 3, 4. That's 500. In case you can't read it, that's 500. So that's the limit to growth. It can't go over 500. So when you make these equations, you make them as y equals 500 over 1 plus, and now there's one equation that says ab to the x, and then the other one is 500 limit to growth over 1 plus ae negative b to the x. I don't care which one you use. I go back and forth. Sometimes I use the left one. Sometimes I use the right one. It doesn't matter at all. This problem asked me to use the right one, so I will. So here we go. How do we make this equation? Well, we already filled in one part. Now, the second part that you have to fill in is very crucial. You always have to start with the y-intercept, or what they call the initial value. So the initial value I can't see. Oh, wait, it's 5. Right? I look at the graph and I'd be like, oh, it's really small, but I know it's 5 according to this. So what does that mean? That means that you have when x is 0, y is 5. So you would have your equation 5 is equal to 500 over 1 plus ae to the negative b 0. Well, anything times 0 is 0. So that's 0. And then e to the 0 is 1. So that's just 1. So really this is 5 equals 500 over 1 plus a. And a little bit of math there tells me that a is 99. So I know a is 99. So good news. We know this equation. And by the way, that would be true for both equations. All right, got a little cut off there, but I'm going to keep rolling. Now I got 99. That would have been true in either equation. So 1, and you guys are probably saying, yeah, that's enough. Let's stop. 1 plus 99e to the negative bx. Well, there's your equation. It could have also been 1 plus 99b to the x, depending on which equation you want to use. Doesn't matter again to me, but they wanted Euler's number on this one. So now the only thing I have left to do is figure out what b is. Remember, an equation's got to have a y and an x in it, and everything else has got to be out. So I need b out. Well, that's not a big deal because now I have this other point. When there's an x and a y, I can plug it in and I can find out what b is, and then I'm done. Because remember, Euler's number e, that's a number. So you can treat it like the number 3. So here we go. I'm going to do 135 equals 500 over 1 plus 99 Euler's number to the negative b times 24. And of course, I'm going to use my calculator, and I'm going to say y equals, do the gross one on this side, 500. Oh, you know what? I'm going to use the fraction button, alpha F1, 500 over 1 plus 99 Euler's number to the negative 24x. And the other equation is going to be 135. And then I will zoom 9 this. Let's see. Zoom 0, I'm sorry, zoom fit. And there's one graph. There's your logistic graph. And there's that one. Beautiful. Now I'm going to go second calculate. That's how sometimes I don't like the fit, right? Intersect. The first curve is the gross one. The second curve is the pretty one. And now I got to move all the way over to where I think that intersection is. And this is taking a lot longer than I want it to. Sorry, but you're having fun watching, right? And then I hit enter and it says, boom, there it is. Your X value is 0.15. So that's our, come back over here. What is that? That's that B value. So it was 0.15. So now I can finally tell you the equation. I can finally say to everyone, y equals 500 over 1 plus 99, Euler's number to the negative 0.15x. That equation is the equation that models this situation. So it's got its limit to growth on top. It's got its constant, or the b value that it has to create it. And if you graph that, you get this beautiful curve. That's how I made the curve on the right side. All right. Have a great day. Stay happy, and I'll see you tomorrow.